हेलो, दिस इज़ कंक्रीट पैथ। तो आज के लेक्चर में हम कुछ प्रॉब्लम्स करेंगे जो आपका मोमेंट एरिया मेथड है उसके बारे में हम थोड़े से प्रॉब्लम्स करते हैं। चलो स्टार्ट करते हैं बिना किसी रोक टोक के। आपका एक सिंपली सपोर्ट बीम है, तो पॉइंट लोड इज अप्लाइड एट L/4 फ्रॉम वन ऑफ द साइड। तो ये दिस साइड इज 3 L/4। तो आपको फाइंड करना है डेल्टा मैक्सिमम। डेल्टा मैक्सिमम इससे पहले जो हमने क्वेश्चन किए थे उसमें हम फाइंड कर रहे थे डेल्टा मैक्सिमम। वो आपका यूजुअली कहाँ पे मैक्सिमम हो रहा था? मिड पे आपका मैक्सिमम आ रहा था, क्योंकि आपकी लोडिंग जो है वो सिमेट्रिक हुआ करती थी। लोडिंग वाज सिमेट्रिक, बट इन दिस केस लोडिंग इज नॉट एट द सेंटर, सो लोडिंग इज नॉट सिमेट्रिक। सो तो आपको ये पॉइंट नोट करना है कि if the loading is not symmetric, if the loading is not symmetric, अगर लोडिंग सिमेट्रिक नहीं है तो जो आपका डेल्टा मैक्स है वो पॉइंट लोड के नीचे नहीं आ सकता। जैसे मैं इसका थोड़ा डिफ्लेक्टेड शेप बनाऊं तो वो कुछ ऐसे आएगा। तो आप देख सकते हैं कि मतलब ये डिपेंड करेगा लोडिंग कॉन्फ़िगरेशन और लेंथ ऑफ द बीम। तो उस पर डिपेंड करेगा कि आपका मैक्सिमम डिफ्लेक्शन कहाँ आ सकता है, और जहाँ पे मैक्सिमम डिफ्लेक्शन आएगा वहाँ पे थीटा 0 होता है। तो इसको हम कोई पॉइंट, लेट्स टेक दिस पॉइंट एज सम पॉइंट के, where let's say this point is k. let's say let this k is at delta maximum, or we can say delta maximum is is at point k. So if the loading is symmetric, if the loading is not symmetric, delta maximum may not be at the may not be at the point where the load is acting. और और ये भी कह सकते हैं कि अगर बेंडिंग मोमेंट मैक्सिमम है और एट द बेंडिंग और द बेंडिंग मोमेंट मैक्सिमम लोकेशन। तो ये ज़रूरी नहीं है कि मतलब जहाँ पे बेंडिंग मोमेंट मैक्सिमम होगा या आपका पॉइंट लोड होगा वहाँ पे डिफ्लेक्शन मैक्सिमम होगी। दिस इज़ नॉट नेसेसरी। सो बट इफ द लोडिंग वाज सिमेट्रिक तो पॉसिबिलिटी है कि मिड पे अगर आपने लोड डाला है तो मिड पे ये आपका डिफ्लेक्शन मैक्सिमम होगा। तो इस क्वेश्चन को हम ऐसे स्टार्ट करेंगे कि लेट्स टेक दिस पॉइंट k where the delta is maximum. So if we make the BMD of this diagram, we can say this is the BMD of this diagram. So this is PAB by L. The equation is PAB by L. आपका A and B equals to P A B by L. That is 3PL by 16. 3PL by 16. और if you want to make M by EI diagram, इसको डिवाइड करते हैं EI से। तो दिस इज L/4, दिस इज 3L/4। तो देयर इज अ पॉसिबिलिटी कि जो आपका डेल्टा मैक्स है दिस इज L/4 पॉइंट। तो देयर इज पॉसिबिलिटी कि डेल्टा मैक्स would be in the right side of that point load P, because यहाँ से आपका थीटा थीटा आ रहा है, तो देर इज लेस पॉसिबिलिटी कि यहाँ पे डेल्टा मैक्सिमम होगा। तो if we assume that if we take that, let this point k is at a distance of x from this side. if we say ये यहाँ से कोई x पे आपका पॉइंट k होगा, तो if we say let's calculate the value of BMD M by EI value at this point k. let's say this point is, यहाँ पे वैल्यू है 3PL/16 EI, और ये वैल्यू था आपका 3L/4 पे। इट वाज 4.75 ऑफ L, बट वी नीड फॉर x x लेंथ। यहाँ तक आपका ये वैल्यू था 3PL/16 EI, बट वी नीड फॉर x length. So we do by similar triangles this value we got. So we can say if we use the moment area theorem 1 that says that theorem 1 आपका कहता है कि theta difference, that theta forward minus theta backward. Let's call this point as A, this point as K, and this point as B. We can say as theta BK, that you draw tangent from B, and with you calculate the deflection at B. Yeah, we can say theta. Yeah, do you draw tangent from B with respect to, so this theta, this means that theta K minus theta B. You can say that theta at K with respect to the tangent drawn from B. If you draw tangent from B, let's say we are drawing tangent from B, so देखते हैं क्या होता है. Let's say that. So if we make tangent from A B such that this value, we know that this value is theta B, this value is theta B, और यहाँ पे theta 0 होगा at the point location of K, theta would be 0 because delta maximum is there. तो आपका theta is 0 because वहाँ पे curve changes that path. तो ये we can say this is theta at K with respect to the tangent drawn from B. Similarly, so if we say what's the area between the two points, theta K, theta KB, that's area between the 2 points, and we can get the value that equals to area between the 2 points. That's area, ये वाला area जो है ये आपको calculate करना है. तो we can say this is 1/2 3p L by 16 EI, and you have x into 0.75 x by 0.75 L, and आपका length जो है x मीटर. तो ये आपका 1 by perpendicular into base, that's your area. But we don't know the value of x. How can we get the value of x? अगर आपको x पता चलेगा तो we can get the delta maximum. So we need to get the value of x anyhow. आपको तो आपने theta b जो है theta kb find किया, but we should get some relation between them, theta kb, and one more relation, that if we get one more relation, so we can easily get the value of delta maximum. तो मैंने tangent डाल दिया, तो is there any possibility that we can get any relation? See, I draw tangent from B. If I say what's this value, what is the name of this this delta, what can I call this delta? इसको हम कहते हैं delta at A with respect to the tangent drawn from B. Delta at A with respect to the tangent drawn from B. What's the relation? If we say this triangle we have formed, that जो delta AB A with respect to B बन गया है, that is equals to tan theta, because theta is small, we say tan theta equals to theta. That's L theta. We can say L theta B. Can we say that? ये आपका theta B है, and this is L, so we can say L theta equals delta AB. So we can say that so we got that theta KB. We know that theta K is 0 actually. This one is 0. So theta B was would be equals to, then we can say minus theta KB equals to this value. So if we take the magnitude, only, so then we can say theta AB equals to L times theta B magnitude. Can we say that? So we need to get the delta AB. So what's the value of delta AB? Deflection at A with respect to the tangent drawn from B, that's equals to centroidal distance from A. This is point A. तो इसका centroid देखना है और इसका centroid देखना है, दो triangles का centroid देखना है, then we can get the, और उनको multiply करना है area, then we can get the delta AB. So let's calculate delta AB. Delta AB, that equals to, let's say first triangle solve करते हैं 1/2 L by 4 3p L by 16 EI, and centroid would be ये जो है distance है, this is the centroidal distance, this one, this is the 2/3 of L by 4, 2/3 of L by 4, 2/3 of L by 4 plus next triangle 1/2 3L by 4, 3PL by 16, 3PL by 16 EI, and we have that the centroidal distance is पहले आपका L by 4 है plus then after that 1/3 of 3L by 4. So we can get the delta AB that comes out to be equals to 5 by 128 PL cube by EI. So but your delta AB that equals to L times theta B. L times theta B. If we substitute that result, that what we call as relation L times theta B. So we can say theta B equals to, but we know that theta B equals to this theta B magnitude equals to 1/2 3PL by 16 and this x square by 0.75 L. So we can get that value, and so we can write that 5PL square by 128 EI equals to जो आपका ये value निकला था. So we write that 1/2 3PL by 16 EI and x square by 0.75 L. So we can get the value of x. So x value comes out to be equals to root 5/4 of L, or we can say 0.559 L. 0.559 L. So we got this value that आपका जो वैल्यू है k जो k पॉइंट है वो पॉइंट रेफरेंस सपोर्ट B से at a distance of 0.559 L पे होगा, तो आपका delta maximum would be there and theta maximum would be there. So we can say to get the delta maximum now. So to get the delta maximum now, we can say delta maximum. We can now calculate that say you draw tangent from B and you say what's this value. You can say this value is delta. Can you tell me what is this value, total value? This value equals to that. We can say that this value equals to we can say this value comes out to be equals to delta at k with respect to tangent at B, but we don't need this value. Actually we need only this part, this part we only need delta at k or delta max. तो इसको find करने के लिए let's make this now again this diagram, deflection diagram. Let's say this was somewhat this way, that this was the load at L by 4 and there was support B, this was A. So आपका K जो value है that's 0.559 L पे, so this is 0.559 L. So this is length of X 0.559 L. तो यहाँ पे point K है, तो we can say, can we say that theta here is 0? Here the theta is 0. If we say theta is 0 here, so we can draw tangent from K. You draw tangent from K, we can get the value of this one. What is this value? We call this value as delta deflection at B with respect to tangent drawn from K. So if we calculate this, what is this deflection at B with respect to K? That's also equals to, if we see, that's also equals to delta max. So you need to calculate delta BK. For that, use moment area method, theorem 2, delta BK. So from this M by EI diagram, we need to get the value of delta BK. So delta BK, that means area between the 2 points. Delta BK, theorem 2, delta BK equals to centroidal distance about point B of the area between the 2 points. So let's say this is the centroid. So this is the distance that xb bar. So we need to get this value, area of this triangle. we have that area of the triangle, that 1 by 2 3pl by 6 3pl by 16 ei. This was for 0.75 length L, 0.75 L, but we have to get the value for x. X value आपका जो है वो that was 0.559 L, and this was the, then we have to multiply it with the length that is also 0.559 L. Then we have the centroid. The centroidal distance would be the centroidal distance, we can say this is our area. This is x equals to 0.559 L. This one जो आपका ये यहाँ पे peak है, that's 3p L by 16 ei, and you have x multiplied with that and divided by 0.75 L. Then we have that centroid up to the point B. This is point K. So that centroid would be at a distance of 2/3 of 0.559 L. So finally you calculate and you can get the value of deflection maximum equals to delta maximum equals to 0.01456 PL cube by 3 by EI. So this is the delta maximum. I hope you got the problem concept fully. Let's take one more problem. So you have a 14-meter beam. Then this is was आपका यहाँ पे एक support है, support A, or support at C, and a point load acting at the free end, that is 30 kilonewton at point D. So what we need to get? We need to get delta at D. Deflection D पे कितना deflection आएगा वो हमें find करना है. Let's say this is 4 meter, ये 6 meter है और ये 4 meter. So firstly you need to get the M by EI diagram. If you get M by EI diagram, we can see what is the deflection profile looks like. So let's calculate the reactions. So by the summation of fx, summation of fy, we can get the reactions that A plus C equals to 180, and summation of moments about C equals to 0. Then we can get the reaction that A equals to 78 kilonewton and C equals to 102 kilonewton. So if you want to make BMD, you can directly make the bending moment diagram, because there are only point loads, so it's easy to draw BMD directly without making shear force diagram. तो आपका यहाँ पे 78 अगर लोड एक्ट कर रहा है तो इस पॉइंट पे it would be a linear variation of bending moment diagram. So that value here would be 78 into 4. 78 into 4. You can write on the side 78 into 4. That is 312 by EI. So similarly, if we say what's the bending moment here? If you see from here, that is 30 into 4 anti-clockwise. So it would be negative 120. 30 into 4, 120. Minus 120. Minus 120 by EI. So बीच में आपका then it would be a linear variation. In this span there would be linear variation because load is downwards, 150 is acting downwards. Then it would be linear variation between the two that span is, that is A B C. That's BC span. आपका linear variation because no shear force remain constant. So आपका BMD linear variation. There will be linear variation of bending moment diagram. So this is the final BMD. Then you divide by EI, you can get the M by EI diagram. So you see here, how much is this value? This length, this is 4 meter length, and this one, यहाँ से भी 4 meter है. So we need to get the, let's call this value as x. we can say uh, we, we can say 120 per x equals to 312 per 6 minus x. So value of x comes out to be equals to 5/3 meter. So yeah, आपका 5/3 है. This is then 6 minus 5/3. So what? So we can say up to this point, the deflection profile would be, let's make it a little bit down. That means up to this point there would be point of contraflexion is there. So we can say this is there would be some point of inflection here. So up to that point there is a positive bending moment. So we can say this is sagging. Then after that it would go hog. So finally we had to get what's the value of, we need to get what's the value of, we need to get what's the value of delta D. So this is the delta D. So this is the delta D. This is the delta D. This is the delta D. So how can we get delta D? If you draw tangent from any point, see we don't know the value of where delta maximum is there. So अगर यहाँ से tangent डालते हैं तो यहाँ पे भी थीटा, point A पे भी थीटा known नहीं है. So and if you draw tangent from, say, we don't know this location, that where the theta is 0, or delta is maximum. So if we say if you take one point common, that's one point that's common between the two spans, that's point C. If you draw tangent from C, there might be some relation between the two spans. So if you draw tangent from C, let's draw tangent from C. This is tangent drawn from C. You can call it as tangent drawn from C, tangent drawn from C. So if we say what's the deflection value of that, so let's say we call, तो इसको हम बोलेंगे this value, this deflection value, and we have one more deflection value, that is this one, that's this one. We can call them that this value is the deflection at A with respect to tangent drawn from C, and this value we have deflection at D with respect to the tangent drawn from C. So this point D has reached यहाँ पे point आपका point D has reached. So from that point we say deflection at D with respect to tangent drawn from C. So we can get these two values if I know, say if I know that what is this total value, if I know what is the total value of this one, let's say we call it as alpha. If I know alpha, we can get delta D. So we can write delta D equals to alpha minus delta DC. So somehow if I get alpha and delta DC, you can get that delta D, deflection at D. So delta D, so that deflection at D with respect to C it's easy. Now this one we can get, that's area between the two, and you have the centroid between centroid from point D. That's easy. So let's calculate that part first. That's very easy now. Let's go for that. So we can say delta D with respect to C, we can say that equals to area between the 2 points, and the centroid about moment of area about the point D. This is point D. तो आपका ये जो centroid है, that's at 2/3 of 4 meter. We can write 2/3 of 4 meter. This is the centroid from D. Then you have area between the 2 points, 1/2. Then you have 120 by EI, and length of 4 meter. So you got, this was point C. So this is the area between the 2 points, and the centroid is acting here. So आपका finally delta DC equals to this value, but overall value is negative. You can keep the negative sign also. So you can calculate it, delta DC it comes out to be equals to minus 60 minus 60 minus 640 by EI. Negative means that negative means that point D delta D so delta D means point D is below reference point, below reference point. Delta D is below reference point C. But but in the diagram, actually point D has reached upwards. Can you see that? Delta D has reached upwards. If when we made the diagram, that means the direction you assumed is not correct for that point D. So actually it should be deflecting in this fashion that यहाँ तक ये ऐसे जाएगा फिर to maintain the slope then slope तो maintain करेगा that theta left equals to theta right, but the thing is it would deflect downwards because of there was some point load here, so it would deflect downwards. That's why negative has came here. But for calculation analysis, we say that delta should be upwards. Then we draw tangent from both the points so to get the value of delta. So finally, D is below reference point C. That means deflection at D is downwards by an amount of 640 by EI. Do you got this? Now finally we got delta DC. What should be the value of alpha? See, we have two similar triangles that this triangle that if you know this value, this triangle is for 4 meter, and same triangle that this one, this triangle is for 10 meter. So we can say alpha is 4 by 10 of, so alpha is 4 by 10 of that delta at A with respect to point C. So we need to get the deflection at A with respect to C anyhow. So we need to calculate delta AC. Calculating delta A with respect to C. That's moment of area about point A into area. Moment of area about point A. Moment of area about point A. So we can see that we have how much areas about point A between A and C. We have one area, next one, and next one. 3 area we have. One is negative. This is negative area. This is positive. So let's take the centroid is that this one is the centroid 1, this one is the centroid 2, this one is the centroid 3. So we can get centroid 1 at a distance of 2 by 3rd of 4, and second one centroid is at a distance of 4 plus this one was actually first one is this one is 5 by 3, so this is 6 minus 5 by 3. That's 18 minus 5 by 3, 13 by 3. 13 by 3 we can write 1 by 3rd of 13 by 3. So third one we can get the value of third centroid from point A. We can write that's equals to, we can directly say that overall यहाँ तक जो point जो length थी that's 10 minus this distance. If we calculate, this is equals to 1 by 3rd of 5 by 3. That's 5. 1 by 3rd of 5 by 3. So actually it was firstly 4 plus 13 by 3. Then we have plus 2 by 3rd of 5 by 3. 9.44. Yeah. we can say that 10 minus 5 by 9, 9.44. That is 9.444. So finally we got this value, this one, and we have this one and this one. So इनको substitute करते हैं between, and we multiply with the area. So we can say first area we can calculate 1 by 2, 312 by EI for length of 4 meter. And centroid act करता है कहाँ पे 2 by third of 4, that's 8 by 3, 8 by 3 plus next area 1 by 2, 312 by EI into length. How much length is this? This is 6 minus 5 by 3 total length. So we can write 13 by 3. So at centroid is acting at 4 plus 1 by third of 13 by 3. This centroid. And third one, after that we have next area, that's negative area, negative triangle, that we can write 1 by 2 minus 120 by EI, and length is 5 by 3, or the centroid is acting at 9.4444. So finally you substitute the values and you can get the value of delta at A with respect to the tangent drawn from C. This value we can get this equals to 4400 by EI. 4400 by EI. Positive here. That's point A is above the tangent drawn from B, above reference point C. That the tangent drawn from A, from C, that's down, and point A is upwards. So we got the value that from the similar triangles we can say now the value of alpha is equals to 0.4 of the value we got 4400 by EI. And finally we can say delta T equals to that's equals to difference of the two. So finally your delta T comes out to be equals to 1120 by EI, positive. So this was a very good problem. We can say that we can calculate this same problem by another method. That's we call as let's keep this problem aside for now. We can solve this problem again by using different method. Let's keep it aside for now. Now next one is that the same method I was saying, telling that. So this method is called as moment area method. But it is moment area method, but we do BMD by parts, bending moment diagram by parts. Say you have this beam, दो मीटर तक आपका UDL एक्ट कर रहा है, और इसके बाद 1 मीटर that's free. So we have 300 kilonewton per meter acting. So we can get the reactions at point A and point B. So after calculating the reaction, we can get equals to them. Reaction we have 200. This one is 400 reaction. So let's say we want to make bending moment diagram. See, in this part there would be linear variation. After that, there is a decrease in BMD because SFD is downwards, so we can have some 2-degree curve. Let's keep this 2-degree curve, and let's say this is 1-degree curve. So this is your BMD. If you divide it by EI, so we can say to calculate the centroids and area, we can say if calculation of area and centroid is difficult, we go with this method. We make bending moment diagram, but by parts. we superimpose the effects of different loads separately, then we finally get the total area that we have that similar. Say let's say that we have only point load, आपका point load का effect आता है that some linear variation, और similarly आपका UDL का variation आता है कुछ parabolic only, then we can have that those formula and we know that centroid calculation also. But for this it becomes difficult to know what's the area of this part. So that's why this method has came into effect. So it says that fix any point, that make any point fixed, make any point fixed, make any point fixed, fixed support, इसको fixed बना दो, फिर वहां पे आपका मोमेंट कैलकुलेशन करना है. let's say we let's say point B, we calculate moments about point B. So if we make point B as fixed, let's make point B as fixed. So this was the same beam, but you made point B fixed. Point B fixed. Then you say, what is the effect of this point load 200 upwards? That's the reaction. We say that there would be if load is upwards, that means moment developed would be clockwise. That's positive moment would be developed, and that equals to 200 into length L. That's 600. That's 600. That is 600. And if you divide by EI, you get M by EI diagram. Then you join the 2 points by straight line. So this is your first that M by EI value about point B. Similarly, you have a UDL also. This UDL is acting after that this span, 2 meter span. If you want to say what's the variation of this, because this is UDL, so we had parabolic variation this way. We can say this value is equals to we can say this value equals to WL square by 2 or WX square by 2, where your W is 300, value of X is 2 meter, on which this load is acting UDL 2 meter पे act कर रहा है, तो 2 square by 2, so that equals to 600. But it is negative. See, the concept behind this fixed making any point fixed is that moments should be balanced about that point, or the moments should be the same. See, point B was simply support, तो यहाँ पे moment आपका 0 होता है. Moment at simply support beam at the end is 0. We can say moment at B is equals to 0. So if you see by this method also, here the value, final value of bending moment at B is also 0. That one is positive 600, next one is your negative 600. So now calculation has become very easy. This is your area 1. Its centroid is somewhere here, and this its centroid is here. This is area 2. We can get the value of area 1, that's 1 by 2. Length is 3 meters, 600 by EI. So we got the area 1. We can get also area 2, that's 1 by 3rd of 600 by EI for a length of 2 meters. So we can get the values, but it's negative. So finally we can get areas directly. And centroid is also, we can say this one, this is L by 3, and this one, this is X by 4. So similarly, this method has came into effect. Now, if we see the previous question now, जो इससे पहले हमने एक क्वेश्चन किया था, उसका अगर हम कैलकुलेशन इसी अंदाज में करते हैं, तो let's say what would happen. Say let's say that let's make point C fixed, because point C पे आपका दो जो अब हमने ये tangent डाला था, that we draw the tangent here, then we get the relation 1, that this delta at A with respect to point C, and ये जो alpha है, हमने वहाँ से एक relation निकाला था कि alpha equals to 4 by 10 of delta at A with respect to point C. So if we make point C as fixed, so let's say we are making point C as fixed from both the sides. So यहाँ से आपका reaction 78 upwards. Then after that you have 150 here, 150 here. So if you do separate calculation, that 170 into length of 10 meter would be 780, and similarly यहाँ से start होगा 150 into 6 meter, that's 900. Negative, this is positive, so we can write here 78 into 10, that is 700, 780 by EI, positive value. And this part we can write this way. This is also linear variation, that this is equals to 150 into 6, 900 by EI. Similarly, if we make point C fixed again, point C fixed again, but from the right side you calculate, from the right side you calculate, there was some reaction at a point load at D was acting, point load D पे act कर रहा था. You can see from the calculation we have, from the problem we have, that 30 kilonewton was acting here. Then इसका इफेक्ट का एंटी क्लॉकवाइज मोमेंट है जो डेवलप होगा 30 into 4, that's 120, that's 120 minus 120 by EI. Now to get now to calculate that delta at A with respect to C, delta at A with respect to C, अगर ये हमें फाइंड करना है तो we would say this is point A, this is point C. Calculate the area between the 2 points. That's area 1, that's area 2. Area 1 into centroid about point A, area 2 and into point centroid about point A. So you got area 1 and we got delta A finally, delta AC. Do we got it? Delta AC. Then we need delta DC. Delta DC says get the centroid, get the area of centroid of that area and multiply with that area about point D. This is your area 3 into, we can say, XD. So we got also this one. So we can get finally delta D. This is very important method when calculations are very lengthy. See, in this previous part we had bending moment diagram somewhat this way. You need to get the area 1, then you need to check how much length is this one x 5/3 जो था आपका आ रहा था. Then you need to say what is this centroid, this centroid, this centroid, this centroid. Then it took a lot of calculation, and this one it tries to minimize those calculations. If the bending moment diagram is area is very difficult to find, or we can say centroid's calculations is lengthy. So let's say one last problem on moment area method. We can use that same concept, that bending moment diagram by parts. So you have this beam. Uniformly varying load after length L/2. So this is length L/2. This is also length L/2. Uniform load acting, uniform load. So this is your W. Okay, this is W. So yesterday we at the end of the lecture we saw that you had this one, then iska be value of bending moment diagram, that's somewhat this way. We know that WL square by 2 divided by EI. Then we have centroid also, we know centroid also. Similarly for this one also, then we say iska bhi value kuch hai WL square by 6, I think ऐसा कुछ होगा. And centroid we can say this is 2 degree, this is 3 degree. Then we were having this problem, that ये वाला problem था आपका, that. So इसको हमने बोला कि let's make it as a equivalent UDL, that then subtract by same amount. This is downwards, this is upwards, W. Similarly this problem is same, but here in this first part of length there is no load. So let's if we extend that, let's extend it to make as a UDL. इसको UDL बनाते हैं. So this is downwards UDL. So finally we got this UDL downwards, but we have to subtract also that same value of UDL. Let's say this was W, this was W. So we had to subtract the same value of W from the downside. So we had to apply upwards load of W. So up to this point, see, up to this point, there was a UDL acting that you applied, a pseudo W acting up to this point for the entire this length L/2. Then after that, you have linear variation. You have linear variation. You have linearly applied that from W to 0. So we can write from W to 0 you are applying. So this is the variation. But still, the mystery has not been solved. So so we can say this part has again came into picture. How can we remove this? So if we say, if we kind of extend it to make it as an equivalent UDL in this form, in this fashion, आपको, if we say let's make it in this fashion also. So if you want to make it in this fashion, you have to extend it by some amount. Say if this value here is W for length L/2, so this one would be, see in this triangle, that जो ये triangle है आपका, this triangle, this we know that from the similar triangles, अगर यहाँ पे आपका W था for length L/2, so if you want to make the similar triangle for length of L, you have to take this equivalent as 2W from here to here. Understand? So you can say this was up to this point, this was equals to W. Correct, this was W, and after that we have one more W. But you have to apply it again in the opposite direction. Say you are applying it upwards, this was upwards. Reference line से नीचे जो है वो that's acting upwards, and जो reference line के ऊपर है what that's acting downwards. So same amount you have to apply in the opposite direction. That here you are applying 0, and after that you are applying a W intensity at the support. So we can say this value is also W. This is downwards. So the final diagram looks like this. So equivalent load, यहाँ पे आपका एक triangle बन रहा है, then after that UDL, then after that a triangle. So here the intensity is finally 2W, here the intensity is W, and intensity is W downwards. So you had this being that this way. You have to get the values that how much moments are that developed at point A. So we know that these are the three diagrams. We know that the centroids and the calculation of area, that we know. Let's say want to say what are the total values of those areas. Let's take this from this point as reference. We say because of this UDL, it's creating clockwise, so there will be negative moment developed at the support, so negative WL square by 2. So we can write WL square by 2, WL square by 2, and the variation would be parabolic up to the length L. So this is 2 degree WL square by 2. Similarly, from the upper this triangle for length L/2, you have clockwise movement developed about support, so there would be anti-clockwise, so that again negative value of we can say again negative value of that's W. Value of this one would be 1/2 W L/2. This is the value of shear force, and it's acting at that this 1/3 of L/3 L/2, 1/3 of L/2. So finally you can get WL square by 24, WL square by 24 up to the length L/2. So you have negative WL square by 24 in a 3 degree curve. We have 3 degree curve, WL square by 24. Then you divide by EI, and उसके बाद जो है same that triangular load of 2W. There is, because of that, the reaction would be clockwise, so positive reaction, that positive bending moment diagram. The intensity would be 2W 1 by 2 into 2W into length L. This is the reaction or shear force, maximum shear force, and you have to multiply it the centroid where it is acting. Or actually it is the total load of the UDL. It's acting at the centroid. The centroid is at L by 3. So that comes out to be equals to WL square by 3. That's positive, WL square by 3. And it is also 3 degree for the entire length. So that's positive WL square by 3. 3EI. We know that centroid calculations for the nth degree spindle. Nth degree spindle, we know that this value comes out to be equals to L by n plus 2. Yeah, degree, why the degree is n, that equals to 3 degree here. So that's L by 5. And the area would be, for the 3 degree, we have BH by n plus 1. That's BH by 4, we can say. 3 plus 1, BH by 4. And for the 2 degree, we have area equals to BH by 3, because degree is 2. Centroid is at L by 1 plus 2. That's, yeah, L by 2 plus 2. That's L by 4. So we can get the values of these reactions. If you want to calculate that what's the deflection at B, the question was actually get the deflection at B. Say this is point A, this is point B, get the deflection at B. Say the deflections would be somewhat this way, load is applied, so deflection would be somewhat this way. So if you draw tangent from A, then you say what is the deflection value here? We can say this is deflection at B with respect to tangent drawn from A. That's also called as deflection at B. So if we want to say what's the deflection at B, we can say get the total area between the 2 points and calculate the centroid about that point B. So finally we can say centroid calculation about point B would be, say इसका centroid यहाँ calculate करना है, that's L by 2 plus 3 degree का होता है L by 5. So we can say 4L by 5, 4 by 5 of L by 2. Similarly for this one, centroid is here, we can say this one, that's 3L by 4. Similarly for this one, that's 4L by 5. And the area, you know, areas we know, we can say this is positive area, this is a negative area, this is also negative area. We can calculate those areas, and finally you multiply with the centroids about point B, and you calculate that final deflection at B, that equals to minus 121 by 1920 WL to the power 4 by EI. You can try it yourselves, because your calculations are your practice is also important. You have to practice yourselves also to make this strong the material very important, strong. You have to practice yourself also. Yeah. And SOM is not a subject of 1 day or 1 semester. It's a continuous process that you have to grow it. You have to grow in the continuous SOM every single day till your career. So this is a continuous process, strength of material. So this was the end of that moment area method. We have already solved in the previous lectures a lot of problems, and these 2, 3, 4 problems were also important for this lecture also. So that's all from the moment area method. See you all. Thank you for watching.